Hello and welcome to another edition from Lofty Labs. Today is going to be a physics edition. We will be reviewing a chapter from Physics and Philosophy, The Revolution in Modern Science by Werner von Heisenberg. Now, a lot of physics students watching this are going to know who he is. If you've ever taken an Introduction to Quantum course, he developed the Heisenberg uncertainty principle from the mid-1920s, the idea that the more you know about a particle's position, and especially an electron's position, the less you're going to know about its momentum. So it's a fundamental limit on your knowledge about a system that you're measuring. So that actually will factor into today's discussion. We'll be talking specifically about the chapter entitled Language and Reality in Modern Physics. And this is basically where Heisenberg just really explores the interplay between language and physics, how physics is communicated either effectively or ineffectively, and how we really perceive the world through language, and how language itself can be a fundamental limit on our understanding of the world. Travis and I, we kind of played a game with this where we both read the chapter by ourselves, and then we wrote our own summary afterwards, and kind of compared to see how our summaries were similar or different. He did tell me that we're going to limit our summaries to 4 sentences. Now, anyone who may know me knows that that's pretty much impossible for me to do. Brevity is not my talent. So I said, you know what? 4 sentences is relative. A sentence itself is relative. Anyone who's taken Latin knows that a sentence can be a page and still be technically a sentence. So, front, back, that's 2 sentences, right? So there we go. All right, so I'm going to read my summary, then we'll flesh it out a little bit, and then I'm just curious to see what you guys think. If you read the chapter too, we're all kind of a community here at Lofty Labs, so just leave your thoughts on the chapter in the comments too, and maybe we can do a follow-up video. Alrighty, so here we go. Heisenberg encapsulates the human conception of the natural world in 2 modes: mathematic symbology and human language. The former is correlated to the latter. Human language, however, is often vague, especially since it can contain implied meanings and the definitions of words are constructed of other words. Philosophers such as Aristotle have sought to categorize the world with precise language, which is based on conclusions and deductions which are logically sound independent of content. But this strict categorization can fail to recognize the nuance and connotations embedded in human verbal communication. Science requires precision. However, so mathematic formalism becomes imperative for the accurate description of general laws. Physics, however, only presents unambiguous definition in the context of a limit large or small enough to approximate classical mechanics. Euclidean geometry is assumed in the limit of small dimension. Lorentz contraction is not a practical consideration in motion measurement in the limit of small velocity, and quantum effects are not accounted for in the limit of objects significantly larger than the atom. However, the quantum limit is different than the Euclidean and Lorentz transform examples because it includes the notion of the interference of probabilities. This notion means that the limit of larger dimensions in quantum theory is governed by the limiting factor of ever-decreasing probabilities as objects scale far greater than the size of an atom. This dependence on probability makes quantum physics appear vague. Physicists often attempt to assist conceptualization by wedding 2 disparate conditions and using them as descriptors. This can seem to devolve into nonsense, however, which drives the physicist back into mathematic description. The language and the logic can seem intertwined, which is why it is so challenging to embody quantum theory in language. A logic which recognizes layers of meaning and complementarity is likely needed. The language of complementarity allows us to describe a potentiality, which has implications for truth statements which would not apply in classical logic. Quantum theory can always predict the result that classical mechanics can, but vice versa is not always true. Heisenberg completes his thought with an exploration of how to conceptualize the underlying physical being behind the seemingly vague language. He finally offers 3 solutions to the language dilemma: use mathematics to communicate, modify logic, or do not use logic. So that was my overall summary. Kind of what I'd like to highlight. First of all, something that Travis and I were really able to kind of flesh out and discuss together that I thought was really interesting and something that we don't always think about. was Heisenberg's assertion that the overall governing laws are quantum theory. So quantum theory itself is the meta, right? But then like classical mechanics, in the limit of large dimensions, it works, right? It works, and it can predict things accurately. You can have analytical solutions from classical mechanics, but it is not limit of large dimensions. Quantum theory would predict analytically the same exact outcome that classical theory would in that limit of large dimension. But then once you get to the very small atomic level, only quantum theory can predict. So quantum theory is the overall; it can predict all things, right? And then classical theory can predict some things in a certain limit. So that's kind of interesting to think about the world in that way. Of course, he also talks about, if you read the chapter as well, you'll know he talks about 3 different limits. The third one being quantum theory, and the limit of very small things, right? So once you start to approach the atomic level. But he also talks about Euclidean geometry having to be assumed in the limit of small dimension. But there he's not talking about atomic level small. He's talking more like, what we deal with in everyday life. When we talk about planes, we talk about flatness, we talk about, one plane being flush to the other. He says that's true in the limit of small dimension, but when you start to talk about like the shape of the universe, right, then all of a sudden Euclidean geometry probably no longer holds true. Then he talks about the limit of the Lorentz contraction, and basically the idea that, this is true in the limit of small velocity, but when you start to approach the speed of light, or, even just a fraction of the speed of light that's, sizable, meaning like, maybe 0.3 c, right? Then you start to have to use the Lorentz transform, right? To account for the let's see, what word am I looking for here? Just the contraction of an item, right? So it looks like it's actually, thinner than it actually is to another observer. So he talks about that limit, and then he talks about the quantum effects. But he also talks about the interference of probabilities with quantum effects, which is a little bit different than just a limit, right? So here, at what we would consider a larger scale, so like what we're used to dealing with in everyday life, it's not the atomic scale, right? So quantum effects could happen at this scale, but the probability is so close to 0 that it doesn't. So, but quantum theory does still hold true, and that probability, that very small probability, is still there. So he talks about the interference of probabilities. And I don't know, I just kind of like to think about things in terms of limits. Even his his seminal theory of the uncertainty principle, that in itself is all about limits. So anyways, that was kind of interesting, but let's see, so how do we connect this back to language? Yeah, he basically was saying that, the dependence on probability, so this interference of probabilities, that, makes the quantum realm unique, right? The fact that we're always talking about probabilities. It makes it all seem vague, like, well, this could happen, or it could be in a superposition of states, or, two things could exist at the same time. This has no ontological meaning to the listener, right? Especially if, they haven't been dealing with the mathematical formalism. They're just hearing you describe this in words, and it sounds vague. And that's so true. If, any of you have taken an intro to quantum class, everything sounds vague at first. It's, you have to actually do the problems, you have to work through the math to be like, okay, well, here's the analytical solution, right? Or here's the probabilities, here's the probability of the of quantum tunneling, right? So you really have to do the math. And if you're trying to explain quantum physics to the general public, he talks about how the way that a lot of scientists in the 20th century have tried to accomplish this is simply by actually describing things in contradictions, which is really fascinating if you think about it. I think that that's something that, you might even, I don't know, I was about to say maybe you could even see parallels of that in religious texts, but I think that's another talk for another day. But it's interesting because he said that a lot of times scientists will try to explain it to others without math by saying, oh, it's like this thing, and then it's like this completely different opposite thing, and then at the same time it's this, or at the same time it's just like the thing that's opposite of that. So it's like they try to use contradiction to explain a very, a reality that's hard for us to conceptualize because, we see it as like a different kind of logic. We see the quantum logic is different than classical logic. So he said that, while scientists will try to do this because they are limited by language, he said that the most precise way to do it is through mathematic symbology. That's the most precise way to describe the quantum logic. But then he also actually says that maybe there's a way through language to have layers of meaning that bring us to a new logic that we can use. That's a governing theory of logic that will apply to both classical and quantum theory. And so he talks about this idea of complementarity. And he talks about some math behind that, the idea of like having like a complex number that would be complementary to another number. And then they would both add up to 1. I couldn't really follow what he was saying. If you guys could, go ahead, feel free to explicate in the comments. But it was interesting because he talks about how the complementarity would let us describe a potentiality, right? Which in quantum physics is very important, especially for something that's, hasn't been measured yet, right? It's still in a superposition of states. So he said that, this could have implications for true statements that would not apply in standard logic. So anyways, that was all kind of interesting how he tried to say that you could do that with language and you could do that with logic and language. And earlier on in the discussion, and in his lecture, he actually talks about how, throughout our attempts at communicating science, we have tried to use reductive methods. Aristotle was trying to categorize everything. So we've tried to develop a language that would actually be logically valid regardless of the content. So, you could have an if-then statement and one would follow from the other, and you could have, this basically use language as a framework for logic, and then the actual content of the language, the nouns, the verbs you're using, they're not really important. What's important is you have this setup, you plug in A, B, and C, and then it all works. So he said that Aristotle was responsible for this originally, a long time ago. At least he's the one who codified it. And then basically he actually goes on to argue that, while that was necessary because we can't have ambiguous language for science and describing things that we're trying to describe with precision, he also says that it actually leaves a lot to be desired because language itself, being a very human thing and the human mode of communication, the chief one, it has all this nuance and secondary meaning that impacts our subconscious responses to things. Just kind of passes through our brain without us completely thinking about it, but it is there. And we're, even the fact that we can't articulate it, it is there. We recognize that. And so that's something that, you can't totally eliminate from human communication. So he does discuss that. He also says that, even the fact that we use words to define words, right? That's what a dictionary is, words to define words. It's really, a dictionary is just kind of a glorified thesaurus, really, if you think about it. So he said that in itself means that language is inherently a vague thing, human language. So so anyway, so this idea, this ability to communicate something as seemingly vague and seemingly illogical. It's not, but it can seem that way at first when you're first learning it, as quantum physics. He says that, maybe we need to develop a language that has that logic, that takes into the account the logic of quantum physics. So that was kind of a really interesting how he started off with just the overall understanding of the limitations of language and the limitations of trying to pin language down, and then he goes into specifically quantum physics, which in his time, when this book came out, it was still like 30 years old. So the fact that, now we need a new way to communicate this that is still precise. And throughout this chapter, he does continually go back to the idea that actually the most precise will be math. And he talks about how math itself, right, it is basically a language because each symbol corresponds to a variable that's being measured in an experiment. I thought that was really cool because a lot of times, especially in a lot of your higher level math classes, and even your higher level physics classes, you stop thinking about the experimental nature of your analytical solutions, and you start to just think of them as just solutions. It becomes very abstracted. And, maybe that's true for some of your upper division math. Maybe it really is just abstracted. But in your upper division physics classes, it should actually always, correspond to a variable that you could possibly have in an experiment. Maybe the experiment would be really difficult to execute, but each one of those variables, it should correspond to an actual physical reality. So that's what he describes when he talks about the actual symbology within math that corresponds to different things. And so he says that mathematic formalism itself is the best way probably to communicate. And that's what he concludes in the end when he says, he finally offers you 3 solutions. You can have, use mathematics to communicate. You can modify logic, so basically develop this, just like you could say, you could predict anything with any physical phenomenon with quantum physics, right? That might be really clunky on paper, but you could, right? Whereas you couldn't actually do that with classical physics, right? So you could predict even classical solutions with the overall quantum formalism, but you couldn't do that with classical formalism. With classical mechanics. The same thing goes for even just the language of logic. And so he proposes that we could modify our understanding of logic and how we use language with logic, with like if-then truth statements, to account for like a quantum logic, right? So that's one of the solutions he proposes. And then the third proposal is just to not use logic, which probably goes back to what he was saying about, the scientists who just use contradictory language to try to get across just the overall high-level idea of a quantum concept. So, all right. Thank you so much for joining this little podcast, and I look forward to hearing your comments. Please read the chapter if you haven't already. And actually, I think Travis is going to be doing a recording of the whole chapter, so you can go ahead and listen to his awesome voice as well. He definitely has a really good reading voice, so make sure you smash that like button. And thank you so much for joining us and for being interested in physics, science, math, engineering, all the best things that keep this world turning. Actually, not really. They don't keep the world turning, but the study of it is pretty darn cool. Thanks, guys.